everyone, and welcome again to Freaky Physics. And we are gonna be live again today with another stream for a review session. Now, for those who are in the loop, you know this already, but for the rest of you, IB exams are starting next week, and physics is one of the first exams. So we will be doing a lot of review for this week, and therefore, we'll be streaming quite a bit this week as well. All right. Another thing that I want to say, and this is a little bit off topic, but well, you see that we do freaky physics at XYZ for the website. We got the .com back, right? So this is gonna change soon. We're gonna go to freakyphysics.com once again. Yep, I unfortunately about a couple years ago I wasn't able to renew the domain and somebody snatched it. Alright, but it's back. They forgot to renew their domain, the domain to their name, and so I snatched it back. Alright, so with that, I'm gonna go into the classroom now. Let's wait for our student. Alright, go. And I think we got, no, this was yesterday, so we don't have new problems. We do have all, we did leave all the relativity problems for today. Oh, there we go. We got new problems right now. So here we go. Let's open these up while waiting. Okay, so we have this. Okay. Alright, that should be easy. The next one. Okay.
Hello.
Hello, Gita, and good day. That's weird. I got a notification after you said hello. Alright.
Sorry?
I got the notification that you were here before you said, after you said hello. So I heard you say hello first, before the beep,
Huh.
before the ding. Alright. How's everything today?
Great. How are you?
Doing good. Well, it's gonna be a busy week for us because exams are next week. Right? So yeah, that's why you booked all those lessons, right? Guess what? My other student who's doing DP as well, doing HL as well, just booked the whole week as well. So it's gonna be quite busy.
Oh,
Yeah. Don't worry, I'm used to it. It's always like this exam season, right? So I'm okay with it. All right. So okay. So I see you sent over 1, 2, 3, 4 new problems. Okay, we'll finish the relativity questions we were doing yesterday first. So the one with all the different problems, and then we'll go to the problems you sent over, and then we'll go to the relativity other once again. All right. Just so it's a bit easier for your brain. Okay.
okay.
All right. So let's start then. So hold on. Let me share my screen now. All right. So this is the problem we kind of like stopped at yesterday. So we're looking for the answer here, right? Okay. The idea here for let's go to E. Okay, let's try to answer E. So according to the rocket, the time that's elapsed is 3 years. Okay, so that's where we will start. In E, the proper time is 3 years. Okay. And then it sends a radio signal back to Earth. Now, when it says what are the coordinates, it's just telling us, it's just asking us what is the time it was sent and location it was sent from. Okay. All right. So in other words, we need to find T prime, and we need to find, this is gonna be from Earth, right? We need to find t prime, and we need to find x prime. Okay. All right. So with that in mind, let's solve for these values. Okay. Um. Okay. Now the time's relatively easy. All we have to do is use Lorentz transformations. All right. So t prime would be equal to t times okay, I let me double check. It dilates, it becomes bigger, gamma t. So
Huh?
we're sorry.
So, but what does it mean, the emission event?
Yeah, basically the idea here is, okay, let's draw this first. This is the Earth, this is the space station, and the rocket is somewhere along this path here. Well, 3, so should be somewhere closer to Earth at the moment, right? Something like that. That's the rocket. So at this point, the rocket sends a signal like that to Earth. The question is, according to Earth, what is this distance here, and how much time did it take to, basically what we're looking for. Let's call that distance
Oh,
x. All right.
also going to be different from rocket R.
From the rocket's arc, yeah, from the rocket's point of view. But of course, in this case, the time's easier to solve because if we look at this, so this is from S, right? If we look at it from S prime, what is happening here? Let's just put it in all into perspective. Actually, no, it's the other way around. Sorry, the Earth is the S prime. The rocket is S in this case. Okay. So S. So in this case, the rocket is stationary. The Earth is moving. Right?
Yeah.
Okay. The Earth is moving at that speed here. So the idea here now is the rocket sends that signal to Earth. Okay. And in this particular case, we know that here the time is equal to 3 years. And we've known earlier that the speed of the Earth relative to the rocket is 0.8 c, right? So this is gonna be this is gonna be 0.8 c times 3 years. Okay, so from our point of view, from the rocket's point of view, this is gonna be, what's 3 times 8? 2.4. It's gonna be 2.4 light years. Okay. Now, we will ignore this 2.4 light years for now because we want to see whether we'll get the correct answer if we use the time first. Well, if we use the time first, definitely we're gonna get the correct answer. Okay, for both L and T. But I'm gonna be interested to see if we get the correct L using this. Okay, now going back here, we know that time here is 3 years, so T prime would be that. So that's gonna be 3 years times the gamma factor. Okay, so that's going to be 1 over square root of 1 minus speed of light was 0.8, speed 0.8 c over c squared, right? So that's gonna be 0.64. So t prime will be equal to 3 times 1 over 1 minus 0.6. Sorry, 0.64. And that's gonna be 3 times 1 over, and that's going to be 3 times 0.36 squared, which is 0.6. 0.6. Okay, and from here we can get that t prime is 5 years. Okay, so we now know the time coordinate. It's 5 years. Okay, now what is gonna be the correct answer though for the distance x? Okay, now remember, we are now looking at Earth's reference frame, so it's not going to be correct to use this and convert this into a new length. It's going to be better if we use the time that we got in Earth's reference frame and find the distance that it travels. Okay, so in this case, x here will be equal to 5 years. So, or rather, x prime will be equal to 5 years times 0.8 c. So that's going to give us 4 light years. C is light, and then years is years, so light years. Okay. So, uh, 4 light years. Okay, so the correct answer will be this: 4 light years, 5 years. Okay. So if we do this more mathematically, so we can say the coordinates are 4 light years, 5 years. But just having those answers of 5 years and 4 light years would be enough in most cases. Okay. All right. Which again would make sense. We will not be using the 2.4 light years here and getting a shorter distance here. The correct way is always to find the proper time first. To use the proper time to get the dilated time. Okay. And then we use the correct version of the time depending on the frame of reference that we're looking at. Okay. Questions?
Okay. Um, it's very confusing.
Yes, I know. The confusing part, what's the most confusing part for you?
It's just figuring out what data I can use for
Okay,
figuring out each.
right. Okay, my tip here is always to find the dilated time. Or, sorry, not the dilated time, to find the proper thing that's given to you, whether it's proper length or proper time. Okay, so let me just note it here first. Okay, so step one,
Yeah.
relativity solutions using Lorentz transformations only, right? Lorentz transformations only. So this does not involve the graph. This doesn't involve the space-time. Was this a space-time interval? Okay, but basically the just using Lorentz transforms only. The step one is always look for given proper value. Okay. Now the second.
It doesn't depend on.
Yeah, it depends on the problem here. Sometimes the proper value could either be time, and in some problems it could be length. Okay.
But it depends on my reference.
Yes, it depends on the reference frame. Okay, but once you know once you know which one has the proper value, whether length or time, you assign that. You assign the reference frame. Assign it to reference frame S. Okay. Okay. So do not assign the proper value to the moving reference frame. Assign it to the stationary reference frame. Okay. All right. So that's the first step, and then the second step is to find either the dilated time or contracted length. Okay. Contracted length, which depends on the proper value. Okay, so what do we do here? Dilated time if proper time is given, contracted length if proper length is given. So depends on given in one. Okay, it's just normal physics. You don't have to do relativity on it. Okay.
Yeah.
All right. Okay, if that hopefully that helps in the exam. I know it's a week and it's a lot to take in, but hope it sticks. Okay.
No other option.
Well, true. No other option. Let's make it stick, right? All right. So this is the next part. Let's go to F. Okay. Now in F, it's a little bit different. You have a probe that leaves the space station towards Earth, and it's got a speed 0.2 c, right? Okay, so So we are gonna determine, according to Earth, when the rock, excuse me, when the rocket and the space and the probe meet. Okay, so let's draw that first again to make it easier to see what's happening, and then from there we can label stuff. So again, that's the Earth. So part F, right? Okay, so that's the Earth, and I'm gonna put the station here. And for now, because the rocket's gonna be moving faster, the rocket's gonna be here. Rocket, right? And also, I'm just gonna write probe here. I'm not gonna make them stick, but that's the idea, okay? Because they intersect, right? Now, from our point of view, let's just do it from our point of view first, okay? Since they leave at the same time, what's gonna happen is I wanna find this distance d, okay? And from the Earth's reference frame, this is just gonna be 0.8 c times time, right? Right? Okay. However, I'm going to, if we're gonna look at the probe, I'm not gonna label that d because I know that the whole thing from the Earth to space station is 16 light years, right? So this is gonna be 16 minus d. All right. Okay. So that whole thing's 16 minus d, and then let's, in this case, the rocket is moving this way, 0.8 c, and then the probe is moving this opposite way. So that's gonna be a negative 0.2 c. Okay. So far clear?
And is the 0.2c given?
Yes, it is.
Okay.
If we go back to the problem, yeah, it's given right there. Okay.
Okay.
All right. So we know, since we know those speeds, also, what can we say about this 16 minus d? This whole thing, 16 minus d, should be equal to negative 0. Yeah, let's use the negative c times the same time t, because it takes the same amount of time to travel from the space station to where the rocket is, right? Okay. So now what we're gonna do is we can do a lot of different techniques, but all of those techniques will rely on getting rid of d. In this case, I think the easiest way to do it is to substitute d in straight away. Okay, so if we do that, that's gonna be 16 minus 0.8 c t should be equal to negative 0.2 ct. Okay, and that should make it easier. Now what's gonna happen here, 16 is equal to 0.8 minus, hold on, did I do a mistake? 16 minus this d equals 0.2 c. 16 minus d. Hold on, I think I may have made a small mistake. Let me see if we can catch that. So this is correct. The distance here is 16 minus d, correct? It's moving that way. 2c times. What if I remove the negative? Is that gonna work? Yeah, that's gonna work. So let's, okay, so I think that's a mistake. We can ignore this negative here. Okay? So let's just keep it positive like that, okay? All right. So in this case, yeah, so this becomes positive. So if we move this to the other side, this becomes just CT, right? And therefore, we know that that 16 is in light years. So what are we going to do now? We're going to look that T is equal to 16 light years over over C. That cancels out with the light on the light years bit, and that's going to give us 16 years. Okay. All right. So now that we got this final version of the time, it takes 16 years to get to it, we can now find this distance d. So d will be equal to 0.8 c times 16 years. And that's going to give us, how much is that going to be? Calculator. 0.8 times 16 is 12.8 light years. Okay. This one's still pretty straightforward in my opinion, except for the fact that we have to look at these distances. Okay.
So the 16 years is from the space station, the probe from the space station to R.
Yeah. So it takes 16 years to travel from the space station to R, or the other way around. It takes the rocket 16 years from our point of view to get to this point. Okay.
Okay, and the equation that we got, it's because we did. Can we go over just one more time how we got this equation?
Okay. So which equation?
The 16 minus 0.8 CT
Oh, this
equals
one,
to
right?
0.2.
Okay. I'm just gonna write the first equation here. Again, we have 16 minus d is equal to 0.2 ct, right? That's from here. Okay. But also, we know that d from here is equal to 0.8 ct. So all I did is change this d to that. Okay.
Oh, yeah.
All right.
Because 16 minus d is the probe's distance, but the probe distance is also the v times time. Okay.
Yeah. All right. Yeah, that's correct. So, is that clear now?
Yeah.
Okay, great. So, we're done with that problem. We will move on. Okay, which one's gonna be a bit easier? Let's go to the... Which one? Okay, let's do this problem first. This is gonna be a very big pace, change in pace here. We're doing the one with the steel ball in the liquid. Okay, here we go. So in this problem, you have a steel ball density, density rho s, and it's attached to a string, fully submerged in a container with density rho l. Okay, the string is cut. What's the initial acceleration of the ball? Okay, so at this point, let's the easiest way to do it is we have to look at the forces on the ball. There are three forces going up, right? And there's one force going down. Going down is mg. This is one of them's the tension, and here it's going to be the upthrust, right? Or the buoyant force. So I'm just going to call bf, fb. Okay, buoyant force. And we do have what's the formula for the buoyant force? That's just equal to the weight of the liquid that it displaces, right? Okay, so the weight of the liquid, that will be equal to the mass of the liquid times the volume of the solid. Okay, now here's the thing though. If this thing has a volume v and has a density m, rho, okay, and also has a mass m, we know that the relationship density equals mass over volume, right? So from here we can move stuff around. We can do the same thing, that volume equals mass over density, right? Okay. The mass of the liquid times the volume of the solid. Okay, so I'm gonna substitute that here. This is gonna be the mass of the liquid times the volume of the solid, and that's gonna be equal to the mass of the solid divided by the density of the solid, right? Okay, so that's the buoyant force right there. Is there something else that we could probably use? This is gonna be the mass of the solid. Let's put that here so we avoid confusion. Okay. In all honesty, I don't know the exact answer. I have to solve this. So we'll just do it together now. Okay. So from here, once you cut off the string, so once the string is cut, we get, we only get tension, we only get the buoyant force and the weight, right? So the acceleration will be equal to the um mg minus the buoyant force all over m. Okay, so specifically, let's put the value in again. There's a solid here, right? So from here, that's gonna be, we substitute this in. So the mass of the solid minus the mass of the solid, the mass of the liquid all over the density of the liquid all over m. That solid. All the mass of the solid gets cancelled out because we can factor out the mass of the solid, right? So we're left with 1 minus the mass of the liquid over the density of the liquid. So here, we don't have the exact answer just yet because our choices, sorry, I missed something. There should be a G here, right? So there's going to be a G here. Okay, so if we look at our choices, all of them look probably more or less the same, but it has a minus, so we can get rid of the pluses, right? So this is going to be wrong. This is also going to be wrong. Now, we don't even have to further solve because we know that the density of the liquid is at the bottom in the denominator. So there's only one choice left where the denominator of the liquid's at the bottom.
B.
B. Okay. All right. Questions?
I got a bit lost when we did. I know, okay, A is equal to mg minus fb over m.
Yep.
But then, how do we factor in the masses?
Oh, okay.
Why would
So,
we do
all right.
that?
I'll just remove that bit so it's easier to follow again. Yeah. All right. So we know. I'm just gonna rewrite that. That's mass of the solid times g. The And then the buoyant force is going to be the mass of the solid, the mass of the liquid, all over the density of the. Is this supposed to be solid or liquid? Solid, right? So S. Okay. Then we're going to divide that by ms. Now, the idea here is both of these have ms. So if we're not going to do the shortcut, we could factor the ms out. Right? So that's going to leave us with g minus ml over density of the solid. Okay. Then we're going to divide that by ms. So that cancels out. Okay.
Okay,
All
I
right.
get it.
What's the mass of the liquid? That's going to be, oh, okay. I think we better do it all the way just to be sure. Okay. So we're left with G. The mass of the liquid in terms of the density, because we need to express it into, but then again we have a volume, right? Mass is density. So the mass of the liquid would be equal to the density of the liquid times the volume displaced, which is the same as the volume of the solid. I'll just call it V. Okay. All over density of the solid. So either way, it still gives us that the solid should be in the denominator. So our mistake earlier, solid should be in the denominator. Okay. So the answer is not B. The answer is D. Okay.
Okay.
All right. So let's just erase that. Answer is that. And therefore the answer is D. Okay. Again, without solving for the whole thing, we got the answer there. All right. Questions?
I understand it.
Okay.
Thank you.
Let's go to the next relatively simple one. Okay, let's do the pendulum, or let's do the mass on a spring. Okay, so mass on a spring. When it releases, it performs. Okay. Between L and H, what's the elastic potential energy? Oh, this should be easy. Okay. Um. Okay. What's the ratio of the elastic potential energy between the two positions? Uh, all right. This, I'm not so sure what the answer is without the marking scheme again, so we'll just solve it. Okay. But think about it this way. In this case, the spring is actually already extended when it's in equilibrium, right? So it's extended when it's in equilibrium here. So, okay. So this has some energy E, right? Okay. Hold on. Let me just double check that. What does the distance E, what does that E over 2 stand for? Equilibrium. Okay, there. That's, we got it. Okay. So I'm going to draw the spring here first, unstretched. Okay. If it's unstretched, then we know that from here to here, the distance is E. Okay. In fact, I'm gonna just a little bit more like that. Okay. So the from here to here is E. Okay. So from here, what is the energy stored here already? What's the energy stored here at equilibrium? So I'll just say equilibrium with P. Okay. In this case, the energy here is going to be 1/2 k x k e squared. Okay. Now here the energy here, and I'm gonna say L here. The energy here at L is gonna be still 1/2 k, but the extension is now E plus E over 2. So that's 3E over 2 squared. Okay. Similarly here, the elastic energy at H, it's, you're gonna subtract the E over 2 from E. So this is gonna be just be 1/2 k. The extension is E minus 1/2 E, so that's 1/2 E squared. Okay. Now, you notice I'm still not solving it. It's because I want the ratio. And when you do ratios, you just go ahead and just do the ratio straight away without solving yet. Right? So that's going to be what's EL over EH. That's going to be equal to both of these have 1/2 K. 1/2 K. So that cancels out. On top we have 3 halves E squared, and this is gonna be 1/2 E squared. Now that means the E cancels out either way, right? So that's gonna be 3 halves squared divided by 1/2 squared. So we just solve that straight away from here. That's gonna be 9/4 times, and then 4 over 1. 4 cancels out. We're left with 9. Final answer is D. Okay.
Oh, okay.
All right. Questions?
No, actually, I don't know why I couldn't solve this.
Yeah. I think the difficult part here is identifying that it does still have it's got energy here. All right, it's still got energy here. So you need to add the energy as it's stretched in equilibrium. You don't assume that the energy here is 0. That's a tricky bit. Okay. All right. Okay. Let's see. We have one. Okay, let's do the 2 questions from the Socos website. Okay. This one is about air sound in. Yeah, the sound question. Okay. So this one's actually the first one about the sound. It's about the sound traveling from air to rubber back to air, right? Okay. Um, you're asked to find the angle between the ray in air and the normal. I gotta ask you something first. Is it given what the speed of the sound in the rubber is? Was it given somewhere before?
No.
Oh, it wasn't. All right. Um, the wave in B is
I mean,
a
I just
okay.
um, I'll
Bec-
try to look.
all right. The idea now that the way to solve this is you're gonna use the Snell's law. N1 sine N incidents and I incident should be equal to NR sine of R. Okay. How does that look like in the data booklet? I think it's gonna be slightly different. Okay, let me just double check.
Um,
Go ahead.
in the previous question, I got that the speed of the sound in a medium was 1.6.
Okay.
Um, and I have to check. But then here it says in the rubber. Before it just said in the medium, so I wasn't sure if that's the same.
Okay, it should
It's
be
a
the same.
continuation.
Yeah, since it's a continuation, it should be okay. It should give what's the speed in that you got again in the previous part?
1.67 times 10 to the 3.
Okay, good. 10 to the 3 meters per second, right?
Yeah.
Okay. So that makes it easier because we have this formula. So we can rewrite this as Ni over Nr should be equal to sine of the angular sine of R, and that's also equal to sine of I, right? But the thing here is um this is also gonna be equal to the velocity ratios. Okay. All right. I think I better not skip that bit. I'll just return to make it easier to see what's happening. Okay. The definition of n. One of the definitions of n is that's gonna be v over c. Okay. Okay. Now in this case, we can simplify this. I will just remove this now because this version of Snell's law works if you know the two values for n. Okay, but this can be also this can be relative only, relative uh to both media. Okay, now in this case you can use the simplified version of Snell's law that n sine hold on, which one is gonna be okay, v over c. Do we know the angle? Yeah, hold on, is that gonna be easier? Yeah, I think it is. So what we're gonna do here is um okay. Okay, in I think I'll just do it like that. Okay? So we're still gonna do I and I sine I. I think it's easiest this way. Now that I thought about it. And R sine R. We're still gonna use this, okay? Now, in this case, our I is the rubber, right? So we're gonna do V the velocity of the sound in rubber divided by some speed. We don't really know what that speed is. This is not light, so we can't use light, right? Some speed in some medium. So let's call this just C. This is gonna be sine of 25 degrees. Okay, that's gonna be equal to the velocity of the sound in air divided by some speed C again. But the thing here is both of these C's are equal, so they cancel out, right? And of course, we do sine of R. Okay, now that we have these values, let's just use that. That's going to be 1667. If we change that to meters per second, that's going to be sine of 25 degrees. That's and then that's going to be equal to the speed of sound in air. That's going to be 340 sine of R. Then just find R from here. So from here, sine R is equal to 1667 divided by 340 sine of 25 degrees. Put that in the calculator and get R. Okay, what's R equal to? Let's go to the calculator. 1667 divided by 340 And then we're gonna multiply that by the sine of 25 degrees. Okay, so that's the sine of r. And then we find the inverse sine of that. That's gonna give us r equals, hold on, that's weird. Okay, let's do that again. My mistake. 1667 divided by 340. Then times, uh, take the sine of 25 degrees. And the final answer is that. And then we do inverse sine. Hey, that's weird. We get an invalid input. Hold on. We may have made one simple mistake. Yep. Okay. Between the air. Okay. Okay. 340
Can I
sine.
ask a question?
Right. Okay. You have okay. 340 sine R. Correct. So what's sine R? It's gonna be that. Okay. It's an invalid input. Now, okay, I should have changed that. This is invalid. So no answer, right? Um no solution for some
But
reason. Do we have a
could
solution?
we have found?
Go ahead. Say it again.
Yeah, I can check.
Mm-hmm.
But could we have found n if we divided the speed of sound by no, if we divided the speed that we got, the 1.67,
Mm-hmm.
over the speed of sound?
That will also work.
Which n would we get? Rubber.
Okay, the thing here is we're not so okay, let me just double think that. The n here would be the relative n. It's not going to be an absolute value for n like light. In light we have values, definite values, right? But with sound it's always going to be relative values that we get. Okay.
So, in the mark scheme, they did sine of 25 over 1.67 times 10 to the 3 is equal to sine angle over 340.
Okay.
And then they get the angle.
Then 7, that's going to be 340 sine of the angle, right? So it's basically like this, right?
They divided.
So this.
They did sine 25 over.
Like that, right? Like this,
Yes.
right? Okay, but basically, this is because this is 10 to the 3. I forgot that. Okay, now that's basically the same thing we did. Think, right? Because if we compare this answer to the formula we got here, that's exactly the same thing, right? But the weird thing here is I'm gonna redo that on the calculator just to be sure. But the weird thing here is it's gonna give us an answer that's bigger than 1. Okay, so I'll do that first. 25, take the sign. That's 42.2 times 1667. Then let's divide that by 340. Is that... alright. We still get an answer bigger than 1. You see? So...
yeah.
So the thing is, if that answer is bigger than 1, this value of r cannot be determined. There is no value that we can get. So this means the sound actually should travel back. It's so r here is no solution for r. No possible solution. So that's what's gonna happen here now is it's gonna be total internal reflection. That's the way I see it, but we may have just missed a particular value. Okay.
Yeah.
Now.
So
Go ahead.
it's because For this question, I was familiar with the equation n1 and then sine of angle is
Yeah,
equal to n2 sine of angle.
yeah.
But how do we get the velocity inside?
Oh, okay. The reason again is if we take this in terms of light, let's do light first. If this was in light, this means we're gonna have to compare that to some speed, right? The speed of light in a vacuum. Now, the
Mm-hmm.
so we're gonna extend that idea that we're going to say that in a certain medium. So in a certain medium, the speed of sound is c. Okay, just like the speed of light in a vacuum is c in this case, right? So
Yep.
this is gonna be the speed of sound in the rubber. This Here's the speed of sound in air, and the c is the speed of sound in some medium. I can actually choose any medium. For example, I can choose water. I can choose, for some reason, I can choose steel or whatever, right? But the point is, these two media should be the same. The reason why we can do that is because once we do that, we can actually get rid of that c by canceling it out in the equation. Okay, so that still works in light as well. So if you have something else that isn't air, so for example, if this were, let's just do it like this were rubber. No, let's do light, so not rubber. So if this was let's just say we have air and we have glass here, and then we have water here, right? So in this case, what we'll do here is n in the glass times, let's say that the light travels that way, right? And glass sine of the incident angle should be equal to the n of the water times sine of the um, refractive angle, right? But going back to the definition, this is going to be the velocity of light in the glass over the speed of light in vacuum sine I. That should be equal to the velocity of the light in water divided by the speed of light in vacuum. Again, that cancels out. So sine I, sine R. So the same idea would work whether we're dealing with light or dealing with sound or whatever other kind of wave. Okay, so the other medium gets to cancel out and we get a simplified version like that. Okay.
And
Um,
um,
Go ahead.
sorry. Is there, because in the maximum, is there a way to get the sine over the velocity instead of multiplied?
No, there's no way for us to do that. So, okay, I really the what we could do though is we can move one of the velocities. So, for example, we want sine I, right? So we can move over the velocity in the glass in this case. So that's gonna be velocity in the water divided by the velocity in glass times sine R, right? So that's exactly the same thing we did here for the sound. We do it for the rubber first. We know the velocity is gonna be faster, sine 25, right? And then we know the velocity in air, it's given as 340, and then we don't know R. So this again, the exact same thing. We're just gonna do the shortcut here. Okay, so that's actually the shortcut. Velocity times incident angle equals the velocity times the sine of the refracted angle. So it's still gonna be the same either way. So the main
Okay.
problem here was this value of 1.667 for the velocity in the rubber and 340 for velocity in air. That's gonna give us a very that's gonna give us a number bigger than 1 if we divide it. Okay, if it were the other way around, we can solve this. If, for example, this was the 340 and this was the 1667, we can solve that because the ratio of 340 to 1667 is smaller than 1. Okay.
Okay.
All right. So yeah, at this point, I think yeah, people, I think that there really is a mistake. I'll be talking to Professor Chocos about this. Maybe it's a mistake.
Okay.
Yeah. All right.
Yeah.
All right. Okay. So either way, we can solve it. It's just that we don't have a value given the problem that we have. Okay.
Mhm.
All right. Um, okay, I think we still have time, but the way let's go for D. Let's see if we can answer that real quick. So let's assume that we have an answer and the answer's in the answer key, right? So
Yeah.
to make it easier for D, let's assume that the answer in the answer key is correct. Okay. So what does it say for the speed of the sound in the answer key? Let's just put it here first. What's this?
340.
No, it is given 340, right? Oh, right, because we were only using angle. So we can use that velocity 340, no problem, right? We know that this sound, and I'm gonna draw the sound as a transverse wave for now. It's gonna enter an open pipe. One end is open, the other end is closed, right? All right. Uh, we need, okay, 340 meters per second. What's gonna be the minimum? Okay, was a frequency given somewhere?
No.
Maybe in A or B?
In A, we had some graphs, but it was only a
Okay.
distance time graph.
All right. So in this case, we're gonna assume that the frequency is given somewhere, but we don't know what it is. So for now, we'll leave it blank. Okay. Let's just say this is given, but we just don't know what the exact value is. Okay. All right. So in this case, we can already guess what the wavelength is, right? So the wavelength here will be equal to the velocity over the frequency. So it's gonna be this divided by whatever given value is, right? Okay. So for argument's sake, let's say that this is I don't know, 150, 170 hertz. For argument's sake, okay. So we can easily find uh the wavelength here. That's gonna be 340 divided by 170. This is already in the correct units, so we'll just go ahead and just say that's in meters. It's gonna be 2 meters, 2.0 meters, the wavelength, right? So if the wavelength is 2 meters, remember that for any, in this case, this is a half open pipe, we will have a node here and we have an antinode, right? And the shortest wavelength, okay, what's the short, for this to happen now, we know that this should be 1/4 of the wavelength, okay? All right. 1/4, or this could be 3/4 wavelength or 5/4 of the wavelength or whatever. But this is the smallest possible length, right? So we will ignore these for now. Okay? Because we'll ignore those, we just go there. That the smallest length is the length is gonna be 1/4 of the wavelength, and therefore that's just going to be 1/4 of 2, and that's gonna give us 0.5 meters. That again, given that that's a frequency. If the frequency is given, if a different frequency is given, we just plug it in here to get a new value here, and then plug this value in here. Okay. Again, that frequency is, I'm giving you the value so that we can solve it. Otherwise, we won't be able to. We can just express it in terms of f.
Okay.
All right, clear?
Yeah.
Okay, that one's done. You still well, we're a bit over time, but you mind extending a little bit now? We'll do
I don't
one.
mind if you don't.
Right, I don't really mind at the moment. We'll do one of those relativity questions that one more of the relativity questions, okay? Which one will we do though? Okay, let's do these two. Let's do the one where determine the scale on the axis of S prime. Let's do this first. Actually, I think all of these problems are related because the graphs all look the same. right?
Maybe they're from the same worksheet. If
Yeah,
it's
I think so too. So anyway, here,
yeah,
let's go to this problem. Determine the scale of the axis of frame S prime. Okay. Um, Here, this is relatively easy again, because all we have to do is use the Lorentz transformations again. Okay. Um, okay. So, oh, I think we needed. Nah. So okay, I think we needed this. So we'll. Hmm. Oh yeah, this is different. Okay. So, what is the scale on the axis of the frame S prime? Okay. Uh, First of all, we know we need to find the speed. The speed here would be equal to the gradient of this line, right? Gradient equals v over c. That's going to be easier to do. V over c equals gradient. So the velocity will be equal to the gradient times c. And now we actually look at the graph and see what the gradient is. We go from 0, 0 here. What's an easy number for us to look at? That's going to be 25. Is that 25? No, 2.5 divided by 2. Okay, so that's going to be 2.5. Does that make sense?
and why is it the gradient of that line? Why not the x?
Okay, because here, the gradient here will be the reciprocal, c over v. Hold on, let me just double check if that's
And
correct. Uh, how fast is it going? C t over v. Oh, it's the other way around. My mistake. But yeah, same idea either way. Yeah. Um, it's the other way
and where
around.
do we get c?
Okay. So what do I mean? This
Oh
is
wait,
c
no.
over v. This is c over v for this, and this is v over c. Okay.
Mhm.
So in this case, so let's use that. C over V is this. So therefore, um, C over V is that. So we'll use this, okay? Equals the gradient. And that's gonna be equal to 2.5 over 2.0. So C over V. So from here, V is equal to C times 2.0 over 2.5, and that's gonna give us 0.8. So that's gonna be 0.8 c. Okay, now that we know what v is, we can now find our gamma. Gamma will be equal to 1 over square root of 1 minus 0.8 c over squared over c squared. It cancels out. We've done this particular problem earlier. We used this percentage before, so we know that gamma is going to be 1 over square root of 1 over 0.6. Okay. If we turn that into, I'll just express that in decimal. That's 1.667. Okay, that's our gamma. So we now know our scale factor. Our scale factor is that. So we can now, on the scales here, what's gonna happen? Yeah, that's it. So we now know our scale factor. What's gonna happen here on the x prime? Um, where's 1 here? It's not so clear where 1 is here, but let's just mark that here. 2 like that, and 3 like that. Yeah. That is going to be 2.5 over 2 is uh 0.6. So this is gonna be 0.6, and this is gonna be 1.2 or something like that. It's not gonna be exact the way we did it because we need to actually measure this with a ruler or something. Okay, but that's gonna be 1.8 here. Similarly here, the time axis scales will be somewhat similar to uh something like this, but this is gonna be 1.67. This is gonna be times 2. This is gonna be 3.33, and then the next one is gonna be 5, and something like that. Okay, so somewhere here it's gonna
And
be 5.
why is the bottom, the x line 0.6 and not
uh
1.67?
okay, because remember that the idea here is time gets dilated, it becomes longer, that's why we have to multiply by this. Okay, but lengths become contracted, so we have to divide by this, and dividing by this is
Ah,
basically multiplying by that, right?
yeah.
Okay, so that's the idea here. So let's note that here. X prime is contracted, T prime or CT prime is dilated. Okay.
And to find that, we do the distance. So if we take the point 2 on the x-axis, we take 2 over
The correct
1.6.
position here would be somewhere here though, because of course we have to measure that actual length to be 1.2. Okay, so that's going to be where
Yeah.
1.2 actually would be, but for now that's going to be good. Okay. All right, so that one's done. Find the use the diagram. Let's do this last one to find the coordinates of event A in S prime. Verify with calculations. Okay, this is gonna be easier the next bit, and we'll end here on this last question. Okay. All right. So here, um, instead of simply kind of guessing where our positions are or where our dilated times are, we can just do a trick here using a ruler. Okay. The ruler trick here is you're basically gonna draw a line parallel to either the X prime or the CT prime lines. Okay. To make it easier, what I'll do here is I'm gonna draw the line here. I'm gonna pick this line here, and I'm gonna go here. I'm gonna make it thick so it's a bit easier to see. Yeah. Okay. Now in this case, the I've copied over the X prime axis, right? And I'm gonna put that over. Just shift that line to where A is, and I'm gonna make it so that the lower edge of the line is on A, so it's easier for us to follow where it is, right? Okay. So in this case, that's the first line. The second line we're gonna draw is gonna be on the CT prime line, like this. Okay. Now, again, we're gonna do the same thing. We're gonna shift over this line so that it is it is on A, like that. Okay. But how exactly are we gonna shift it? There. Somewhere there. Okay. So, the reason why we do that is basically we're just making these. You see here on the CT and X CT versus X, right? For S, our grid lines are perpendicular to each other, right? What we're doing here with these lines that we did is we're doing the grid lines. Okay.
But what does it mean if something is on the same grid line?
If they're on basically, okay, so here, if we ignore what we drew first and we just look here at A, then if we look at the grid line, then that means event A occurs 4 meters away from our observer, and it was observed around 3.6 seconds away, or something like that. Okay. All right. So the grid line just tells you what the coordinates actually are. Okay. Now, because of these two axes here not being perpendicular, the grid lines themselves are also not perpendicular. So, but what we're doing basically is we're drawing those grid lines so that we can see on the axis where they are. Okay, so A, according to this diagram, is on the CT prime value here and on the X prime value here. So we can kind of guess what calculate. We can now kind of guess where that is. So that is gonna be approximately, well, if we put a ruler out and draw and, well, not put a ruler out, but if we look at the values later on with the grids, we can see what this value is. Okay, so just a good estimate, this is gonna be around 3.3 times our gamma, divided by our gamma rather. Okay, so this is this time around this, and I'll take the line out. So this was the position here. That's our position on the X, right? So in this case, X prime would be approximately 3.3 times divided by the 1.66 or 1.67. Okay, then here on our Y, this is gonna be our CT. Just here, our CT prime will be approximately equal to what value is this? Approximately equal to 1. Sorry, this one, 1.2 times 667. That's the approximation. The correct value would be to actually use the Lorentz transformations. Okay?
Okay.
All right. So again, these are grid lines. We normally draw grid lines perpendicular to each other, but because grid lines themselves are not perpendicular, we have to shift the point of view, so to speak.
Find the position, we draw parallel lines to see where they intersect.
Yes.
The axis.
They should intersect. Those lines should intersect on 2 points. One on the axis, and the other point would be on the event. In our case, event A. Right?
Okay.
Okay. So tricky, but once you see once you understand what you're doing, you're just making grid lines. It makes sense. Yeah.
Yeah.
All right. Okay, so we'll end here, and we still have 3 relativity problems here, but I think we can do these other ones tomorrow again. Yeah.
Okay. Yeah.
Just send over some more problems as well. Okay, so that's it for today. We went over time a bit, but you're okay with it, so thank you. We'll end here tonight for me tonight. Okay, so one more thing. Can I ask for a favor? You haven't left a review yet, right?
I feel like I did, but I can do it.
I can double check, but either way, if you haven't, can you hold off for now? Wait until you get your results. When you get your results, that's when you make the review. All right.
Okay.
All right. Okay. I'll double check either way, and then we'll see there. Okay. All right. You have a good evening or good day. I'll see you tomorrow.
Okay. Thank you very much.
Bye now.
Have a good day.
So yep, that's the thing there. Okay. Jasmine and Mariamana. Oh, sorry, I didn't change it. I'm so sorry. I was streaming the whole time without seeing it. Sorry about that, if you're still there. Alright, I forgot to do that. Man. Alright, it's fine though. Me talking, I still have my notes. I can transfer this over later for for like videos. Okay. Alright, so again, guys, if you're still there, I am so sorry. I forgot. That's on me. Alright? But anyway, thank you for being here. For coming here and looking at it. Alright. Well, I can just show you the work real quick. The last part at least. Okay? So when you're doing relativity, basically, let's take a look at this. These black lines, these are from the non-moving reference frame, the stationary reference frame. These red lines are the uh, reference frames axes for the non-stationary or the moving reference frame. Okay, and then the shortcut is that the for this, it's still here, yeah. Okay, so the gradients of these lines would be basically be connected to their speeds. Specifically for the CT prime graph or the CT prime axis, yeah, it's gonna be the gradient of the CT prime axis would be equal to C over V. Okay, so from there we can get the velocity, and from the velocities we can get the gamma factor, the Lorentz factor. Now, once you have that, so that's one way to do it. Another way to do it is by doing this one little trick. So here on the CT prime and the X prime axes, they are actually the axes of the moving reference frame. So you can make grid lines, but because our axes, so to speak, are not perpendicular to each other, the grid lines themselves would not be perpendicular to each other. So you will have to do one of two things. The first thing, and the thing that's the thing we did here, is that for these lines, these are the grid lines according to these axes. The other thing you can do, and that's the more difficult part, is we can shift these over. We can move this X prime so that it's gonna coincide with the X. We can move the CT prime so it coincides with CT. But all of these points and these axes and these grid lines will also move along with them. Okay, so that they're gonna be perpendicular. You kind of see what's happening here, though. Uh, so that point A, that event A will move along, but these will not move anymore. These intersection points here on the axis won't move. I'll just give you more later on. Hopefully we can do some problems tomorrow again. Okay, so again, for those who are still on the stream, I am so sorry about that. I forgot to shift over to the board. But uh, if you were still listening in, hopefully you learned something. So for now, we are done. So we're going to say goodbye. But before we do, don't forget to like, share, and subscribe to the channel. We're on YouTube, Facebook, and TikTok and Instagram. And again, Instagram and TikTok, I think, no, sorry, not TikTok yet. But I think on Instagram, announcements are coming up whenever we go live or whenever a video is up. So follow there for announcements. And also when we go live, we are on Twitch. We'll end here today. So with that, I will say for everybody here who's still listening that I hope you have a good day, good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everyone. Bye bye now.